Okay, now our part of the project is to talk about mass as a characteristic of the family in the universe of stars. So, just like in the snapshot here, everybody's a different weight or mass. So it bodes well for that as well. When we originally talked about mass, we talked about the sun's mass and how to derive that. And we will use some of those same methods in deriving masses of stars, but let's get into that gradually. When we talked last time about the 20,000 closest stars to the sun, we talked about the line, the main sequence, which really concentrates on luminosity. And we talked about the red giants. 90% of our stars in our universe seem to be along the main sequence. Let's see what that main sequence has to do with mass. Actually, mass is a big part of the main sequence. The main sequence is based on luminosity that is equal to the luminosity of our sun, which is at 1. But if we look at that beautifully along there, mass is also correlated. And there are low masses at low temperatures and low luminosities along the main sequence. And there are higher masses at higher luminosities and higher temperatures at the sequence. Remember, temperatures go higher the closer you are to the intersection of the X and Y axes. And those masses increase as you get up near the blue giants that are up in this area. So there is a correlation along the main sequence of mass. Really a beautiful thing. And when we found the mass of our sun, we did it in a process that was actually dates back to the 1800s. And we did it in part based on the transit of Venus, if you remember. So we used parallax to get the distance to Venus. We used the transit to get the diameter across the sun. We use the sphere formula for area of a sphere to get the volume of the sun, which was based on the diameter of the sun. And then from there, we were able to get the mass of the sun. Let's take a look back at how we did that. That was done by a tweak on Kepler's third law. Remember, Kepler's third law equilibrated orbital time in Earth years squared to the distance between the sun and another planet cubed. And that was done in astronomical units. So that this was a proportion that didn't have kilometers to it. It didn't have miles to it. It was in astronomical units. And that was fine back in the 1600s and the 1700s when we didn't know what those units were. And at that time, Newton said, you know what? That's fine to look at the sun and the planets, but gravity is universal. So we should be able to put the center of gravity between two objects as part of this equation. And what he did a tweak on Kepler's third law, made it into Newton's law of universal gravitation, and he took Kepler's third law and divided this side of it by the mass, the total mass of a system of two objects, meaning that the mass of one object is attracted to the other. Ma equals ma. So the mass of the sun and the acceleration of the sun to the earth equals the mass of the earth and the acceleration of the earth to the sun. So he did a calculus derivative, and he reorganized Kepler's third law to say this. It helped us to achieve the mass of the sun, and we were actually able to do that by calculus with kilometers associated with that. So that's how we initially looked at the mass of the sun, and now we can go and say that that sun is a solitary system. We have one star in our solar system, but for most stars, they are in binary solar systems in our universe. Sirius A and Sirius B, Rigel A and Rigel B. Those are binary star systems. Very, very common. They rotate around each other. So these star systems rotate around a common center of mass, much like you see in a seesaw. Before we get to that, I'll just show you how this works a bit. There's a center of mass for two stars, star A and star B. And this star, star B, looks brighter than star A. And in fact, this star that is in star B is brighter, and it's more luminous, and it has more mass, and it's hotter as well. And as a result of having more mass, it is going to have a tighter orbit around the center of mass. And star A, which is not as luminous and not as large, is going to have a larger orbit around the center of mass. But both of these stars in this binary system are going to orbit a center of mass. There are three types of binary systems. There are visual binary systems, spectroscopic binary systems, and eclipsing binary systems. Each has a little bit of a different way to find the mass of that system, but let's explore these different systems right off the top. The visual binary system is something that you can definitely see. In fact, these are photos taken over time of the binary star Kurger. And you can see a larger star and a smaller star. And you can see the smaller star orbiting. It's a little harder to see the larger star orbiting. The center of gravity for this star system is probably very close to the big star. And what you note here in a graph of the data is that you're seeing this small star orbiting the center of gravity, which is probably right around here. And here's 1948, 55, 60, 65, 70, 75, 83. And at the same time, this larger star is probably orbiting at about this area around the center of gravity. When we look at another type of star system, the spectroscopic binary star system, these are star systems that by a telescope are seen as one bright star. They are not seen as two stars. And when you point the spectroscope toward that star, you see something change and you see a Doppler shift that indicates there's a second star in there that is causing a change in the orbit. Let's look into this a little bit more. Here's the lab reference of this spectra, which is probably a luminosity class in the main sequence. And the reason I say that is because these lines are pretty wide. We talked about luminosity and the width of these lines and luminosity classification. This is the reference. And from the reference, you start to see these lines in the infrared wavelength shifting. And you start to see the blue line shifting. Everything is shifting toward the red. That's called red shifting. Now, I apologize that this particular spectrum doesn't have the blue on the left like you're used to seeing and the red on the right. But I think that you can grasp that you won't always be seeing things this way, and that when you see a spectrum move more toward the red that is red shifting. When you think about moving more toward the red, you're thinking about moving more toward a wavelength that has less energy at infrared. When you think about the ambulance coming at you with a siren, and as it's coming at you, you hear the very high frequency, high energy siren. When it's going away from you, you hear the lower frequency and the lower energy siren. Red shifting means that the energy is dissipating. It means that the star is moving away from you. So this is motion away from the observer that causes a red shift. You would, if you were looking at this star system from this vantage point, in 1965, you would see a red shift as this smaller planet moves away from your eye. And conversely, you would see a blue shift, meaning that from the reference, these lines seem to shift toward the blue when this smaller star starts coming toward your frame of reference in the 1980s to complete its orbit. So that is how we tell about spectroscopic binary star systems, red and blue shifting. When it comes to eclipsing binary star systems, these star systems transit the star, much like Venus transits the sun, so that when we look at the star with the telescope, we seem to see one star. When we point our photometer to the star, which is like a photography device, but it's a photometry device instead, we can see that the intensity of the wavelength or the intensity of the brightness that we are recording over time dips when the smaller star goes dead on at an angle across the larger star. So there's a dip here that prevents the bright star from showing all of its light because it is eclipsed. And then there is another dip here when the orbit comes back around again. Eclipsing binary star systems tell us a lot of information, much like Venus told us so much information when it transited the sun. I really told you all about that, and I told you all about that too, and I told you all about that. So I think that we are ready to go on to more information about spectroscopy and about mass.